time on the practice problems because I think that'll be probably most useful to you guys. Also, Sal told me that my presentations are boring and I need pictures of something, so I have a picture of a rocket. That's the only picture, though. All the rest of the slides are boring. Okay. This overview slide is actually totally inaccurate. Okay, we'll continue moving on. So you guys have seen lots of assembly at this point, right? You've now actually completed BOM. So this should be nothing new. If you see move L, 8 RBX, EAX, we can break that into parts, right? Move is the instruction itself. That L is a suffix denoting the size that's going to be moved. We'll talk more about that later. And then we have 2 arguments to the move. We have a source and a destination. And those parentheses in that 8 is a special addressing mode that controls what we do with that source register. We'll talk about that more too. So same rules apply for the final as for the second midterm. You'll be given our handy one-page guide at the back of the exam, so you don't have to memorize any of this stuff. And we're going to be doing I'm going to be talking about a lot of things that you don't necessarily have to know for the final either, because I think it's useful as practice to think about how the compiler actually would generate assembly code, and it's useful to understand what's going on, but you won't ever have to write assembly code on the final. You'll only be reading code and interpreting it. So just a heads up. And I pointed out that typo in my last presentation, and it's still there. We'll probably fix it next year. Okay, so talking more about move. Move is the most important and the most popular instruction. And it's really easy to read because you're moving the source into the dest. So the source comes first, the dest comes second. Important to note, though, that move doesn't change the source at all, so really I would have named this instruction just copy, because that's what it really does. And what makes move really useful and versatile is the different addressing modes. So we'll talk about that. So we'll talk more about registers more later too, but a big part of efficient assembly code is getting data where it needs to be so that we can work on it quickly. So that involves a lot of moving things into registers and out of registers, and moving things between registers and memory. So we have different addressing modes to do different tasks like that. Simplest is immediate mode. If you're moving a constant into a destination, usually a register, then you can just specify that number, and that number, the constant, has to start with a $sign.
Is there a difference between direct and immediate mode?
Yes. Good question. We'll get to that. Direct is the third one. Register mode is like immediate mode, but we just name a register instead. So in register mode, you're moving the contents of that register into the destination. So if EAX is a register, it has some number in it. We're moving that number into the destination. Direct mode looks a lot like immediate mode, but it doesn't have that $sign. And the difference is if there's no $sign, then it's not a numeric constant, it's a memory address. So direct mode means go to that address in memory and move the thing at that place in memory into the destination. Then we can get fancier. Indirect mode. Indirect mode is to register mode as direct mode is to immediate mode. So rather than moving the value in a register, we're moving the value pointed to in memory by that register. So if RDI here has an address, then this first one will move. It will dereference RDI to get to a place in memory, and then it will move from that place in memory into the destination. Yeah, question?
So what happens if the address is not a valid address?
If RDI does not have a valid address and we try to do this, then you'll probably segfault, just like you would if you dereferenced an invalid pointer in C. So if you see something like, because you know the assembly was generated by GCC and GCC usually knows what it's doing, if you see something like this with RDI in parentheses, that's a good clue to you that RDI is a pointer, because the parentheses with a move means that RDI is being dereferenced. So if you're trying to guess what the function that it includes this line is doing, then whatever variable RDI represents is probably a pointer. And you can also give a numeric offset in indirect mode, so that will dereference the pointer and then add that offset. Yeah?
So direct mode, is that a dereference?
It is, yeah.
Then what would you do if you just wanted to copy the address?
Then you would put a $sign in front of it, and then it would become immediate mode. Yeah. It's easy to get those two confused because the $sign is a little bit subtle, but it's also usually clear from context. Something like 10 does not make sense as an address, for example, and if you see something in direct mode that looks like an address, then that also makes sense. Yeah?
The arithmetic and move is always in single bytes. It's always bytes.
The offset, yes, is always in bytes. So this 8 parentheses RDI means RDI plus 8 bytes is where we start copying from. So yes, good. It's never scaled by something else. Any numbers you see are always in bytes. Speaking of scaling, this is the most complex. Here, if you see multiple things inside the parentheses, that's indirect scaled mode. The first thing in parentheses, RSP here, is treated the same as like the RDI up above. That's like the base address. And then RCX, or whatever the second argument is, added to it. And if there's a number given, then that number is a scale for the second argument, the second thing in parentheses. So this would mean RSP plus 4 times RCX. And the scale can only be a few things. So this is basically how array indexing in C gets converted to assembly. You can think of RSP in this example as being the base of the array, and RCX as being the index, and maybe that 4 is the size of each element. So then RSP plus 4 times RCX would be the address of the RCX element in the array, right? And just like with the other parentheses, we're dereferencing the result. Yeah.
So in the indirect mode, can this or the offset be anything?
In either of the indirect modes, the offset can be anything, yes. It can also be negative.
Like only the scale has to be 1, 2, 4, 8.
Yeah, the scale can only be 1, 2, 4, 8. And if you think back to the bits assignment, part of that you were parsing assembly code. And you might remember that you dealt with a scale in that assignment, and the scale was stored with only 2 bits. So there were 4 options for the scale, and those 4 options correspond to 1, 2, 4, and 8. And then you can also omit the scale, and then it's just implicitly 1. Cool. This is a really dense slide, I'm sorry. Okay, other instructions. These are mostly pretty straightforward. Again, you give a source before a destination, and the result of something like an add or subtract is always stored in the destination. So it's like doing destination add source dest is like doing destination plus equals source. You can also subtract, multiply. There are bitwise operators, of course, and there are shifts. Assembly, we make a distinction between a signed shift and an unsigned shift. In C, that's implicit. If you shift a signed number to the right, it does a signed shift in C. If you shift an unsigned number to the right, it does an unsigned shift. But in assembly, it's explicit, the difference. So a signed right shift pads the left side of the number with the signed bit, so that if you right shift a negative number, it stays negative. An unsigned shift always pads with zeros.
Does that mean if you had like if we have an int that's unsigned or assigned int, if it was a negative number that was like a negative signed bit, like 1000, when you like shifted it over, if it was unsigned, it'd just be a 1000. If it's a signed like right shift, does it keep that sign and like just have like, I guess, what happens if you, does it always preserve the sign bit even if you like shift information into there, if that makes sense?
With a right shift, it'll always preserve the sign bit. So remember, a right shift is shifting things off of the least significant bits. So it's padding it from the left side where the sign bit is.
Oh, I'm sorry, yeah. Right.
A left shift always pads with zeros. There's only one kind of left shift. So if you left shift a negative number, if you shift it far enough, you might move a 0 into the sign bit, and then it wouldn't be negative anymore.
Okay, yeah, that was my question. You can like push a 0 to the sign.
That is possible with a left shift, yeah. Cool. All right. LEA is probably one of the most confusing instructions, not because it's that weird, but because GCC loves to use it in weird ways. So the original intention of LEA was to be like a move, but without the dereference. So it does all the same pointer math without actually going to memory. So like here, base IDX scale, that's that scaled indirect mode. So it would do base plus IDX times scale. But then rather than dereferencing that, it would just store the result of that addition and multiplication into the destination. So that's useful for addresses. If you want to get the address of some element in your array instead of getting the element itself, then you can use LEA. But it's also really useful because GCC can do lots of other things with LEA. Because that addressing mode lets you do an addition and a multiplication, say, in the same instruction, which is much more efficient than doing them separately. So you might see something like this first example, which is adding 4 to RSP and then storing the result in RBX. Now, can anyone think why GCC might do that first example instead of using an add instruction? Okay, it's pretty much the same example as the second one. Answer is the second one, actually. If you add 4 to RSP, RSP would have to be the destination, and it would store the result in RSP. But if you don't want to change RSP, if you actually want to store the result somewhere else, then LEA lets you do that in one instruction. Otherwise, you'd have to do the add and then a move. Same thing for the second example. You can use LEA to add 2 registers together and store the result in a third register. And again, it saves an extra move if you need the result in a third register. And then it can also get tricky about multiplication. Remember, the scale can only be 1, 2, 4, or 8. But if you add a number to itself scaled by 4, that's the same as multiplying by 5. So GCC for small multiplications will sometimes do tricky things like that too. But in every case, if you just parse the LEA using the same addressing modes that we talked about, and remember that there's no dereference, then you'll get the right answer.
There's no dereference, so what does 5 times RAX mean?
If RAX is a number like 10, then that will store 50 into RBX. So in these examples, the sources don't have to be pointers. They could be any number.
The base, you mean?
Yeah. Normally in move, the base would be a pointer because it has to be dereferenceable. But with LEA, we're not dereferencing anything, so GCC will sometimes use LEA even when it's not working with pointers. So RAX in this last example could just be any number, and this instruction will multiply it by 5. Cool. Yeah?
How does GCC do division?
Division is hard. Division by powers of 2 you can replace with shifts sometimes. Otherwise, it just has to use the division instruction. So there's an IDiv for integer division, just like there's IMUL. Yeah. Oh, so the other important part of this is the reason it would even think to use LEA instead of just multiplying is because multiplication and division in the general case are much more complex than adding and subtracting in LEA. So like as a general rule of thumb, a multiply takes about 3 times as long as an LEA instruction or an add instruction. So if you can replace one multiply with one LEA, then you're saving time, even though it's still just one instruction. Okay. Cool. You guys have seen a lot of these too. Usually we see comparisons and jumps right next to each other. So that JLE at the top there is a conditional jump. It jumps based on some conditional flags that are set by the compare that happens right before it. So if we compare A and B, it jumps if the second number is less than or equal to the first number because it's JLE, jump less than or equal to. So it jumps if B is less than or equal to A. Note the order there, right? This is also really easy to get backwards. I don't know why it does B from, or it does B minus A instead of A minus B. So compare does subtraction, test does anding. So if you see a compare and then a conditional jump, then things are usually pretty intuitive. Like that example, jump if B is less than or equal to A is the result. If you have a test, like here, the second example, then you'll have to think through it a little more carefully because test takes a bitwise AND of the two operators and then sets the flags based on that. So if you have test AB and then jump equals, that means we do A and B. And jump equals, if you look on the cheat sheet we'll give you, means it checks if the 0 flag is set, which is only true if the result is 0. So it means jump if A and B is equal to 0, which would mean that A and B have no on bits in common, right? No ones in common. Okay, and then the third example is intuitive, but if you also want to like parse what it has on the cheat sheet, SF is the sign flag, OF is the overflow flag. So if the sign flag is not the same as the overflow flag, that means we have two cases. Either the result is negative, which makes sense. If B minus A is negative, then B is less than A. Or it means the result is positive, but we overflowed. And if it's positive, but we know we overflowed, then it means it should have been negative. So that also would mean that B is less than A. So that makes sense. Cool. Okay, and then there are a few more instructions that are like combinations of others, just for convenience, that you'll see. Push and pop are really useful for putting things on and taking things off of the stack. And what they do is they move something onto the stack and they update the stack pointer all at once. And that way the stack pointer always points to the bottom of the stack. So push will take that source and put it onto the stack. Pop will take whatever is on the stack and move it into the destination. And then when we call a function, we use call and then we give it the address of the function. And what that does is it pushes the instruction pointer. The instruction pointer, we'll talk about that later too. The instruction pointer always refers to the address of the instruction we're currently executing. So if we save that by pushing it to the stack, that means that when we return from the function, we can remember where we left off, and we can return back to the instruction we started from. And then after you save the instruction pointer, you can jump into the new function. So that's basically what's happening there. And then return goes back. And to go back, all you have to do is pop the old instruction pointer. So it was saved on the stack by call, and then when you return it, pops it and updates the instruction pointer. Anyone have a guess why there's no jump in the return like there was in the call? You guys are a lively bunch tonight. So if we just updated the instruction pointer is used to figure out where the next instruction should be. So if we update the instruction pointer, then automatically we'll go back to the right place when we execute the next instruction. So you don't have to have an explicit jump there. And this is not exactly how it's implemented, but it's what it's equivalent to. Okay. Any questions about the instructions? Cool. Yeah?
For when you don't have to jump back to the, when you're returning, why is that different than when you're calling? Because you're both repeating instructions. So why would you jump when you're calling?
Because when we push the instruction pointer, we're not changing the instruction pointer at all. We're just saving its value. So by default, we would still move to the next instruction in the calling function. But what we want to do in that case is jump into the function we're calling. With return, we're updating the instruction pointer, so that happens automatically. So the other moral of the story here is that if you were writing your own assembly, you probably shouldn't mess with the instruction pointer on your own, because that can cause really weird things to happen if your program starts jumping around with what instructions it's executing. Oh, and of course, internally that jump is updating the instruction pointer too, right? So what that jump means is basically set the instruction pointer to that address, and that's how the jump happens. Yeah, okay. So it turns out that CPUs have been getting faster much more quickly than memory has been getting faster for decades now. And as a result, CPUs these days are way, way faster than RAM. So we need ways to bridge the gap so that we can store things close to the CPU and be able to use them quickly instead of having to wait for RAM all the time. So there are two ways we do that. First, by putting registers right in the CPU, and second, by adding caches, which are beyond the scope of 107. So we have a few registers built into the CPU, and they're very, very fast, so we can access them in like one cycle, instead of RAM, which is far away physically and also requires a lot more logic to access, so it's slower. So the different registers have different purposes, and we will talk about those. And registers can be call E saved or call ER saved, which we'll also talk about. Cool. So before we get into that, though, let's think about how the register names happened, because they're completely unintuitive, right? So like 40 years ago, I assume this is what happened. I don't actually do any research for these presentations at all. So initially, CPUs were much simpler. We only needed a couple registers, so they started out with 4. And they lettered them A, B, C, D. That's nice and intuitive, right? Okay. And then they decided to add some registers with specific purposes. Like SP is the stack pointer, BP is the base pointer, IP is the instruction pointer. It makes sense to give those descriptive names, so that's great. But typing is still hard, so there's still short abbreviations, of course. Okay, and then once we started making 16-bit CPUs instead of 8-bit CPUs, we needed a way to distinguish the 8-bit registers from the 16-bit registers. So we renamed the 8-bit versions, and we renamed the 16-bit versions. So now they're distinguishable, but now you can still reference the 8-bit ones, so you can still run 8-bit code. Okay, and then we had to do that again when 32-bit CPUs came out. Then we had to do that again when 64-bit CPUs came out. So now we have lots of different names for the different sizes of registers. So for example, EAX is the lower 32 bits of the 64-bit RAX register on a MITH machine, because MITH is 64-bit. Okay, and then when they expanded to 64-bit, they also added some more registers, and they gave up on letters at that point, so they just numbered them. So that's why there are these weird registers tacked onto the end, like R8 through R15. Okay. So all told, there are about 16 registers that your program can normally access. There are, in practice, a lot more than that on the CPU. But beyond the scope of 107, I can say that for everything almost. Okay. So one of the most important things we use registers for is passing parameters between functions. In x86-64, the convention is that the first 6 parameters get passed in 6 specific registers. So RDI is the first one, RSI is the second one, RDX is the third one. They're all listed in order on the cheat sheet. But not all functions take only 6 parameters, so if there are extra parameters, then we might have to put things onto the stack. So any extra parameters that don't fit in the registers, the calling function, the caller, I should say, will push it onto the stack, and then the callee can read them from the stack. And then you saw this in lab too, a large parameter like a struct. Sometimes GCC will get clever and split it into multiple pieces so that it can still fit in the registers. So if you have a 16-byte struct, you can split it into 2 8-byte chunks and store each chunk in a register. So if you're looking at an assembly function, how would you guys guess how many parameters it takes? Yeah, any ideas?
Which ones get set before the function is called?
Yeah, that's a good idea. You can look at where the function is called from and see which registers are set. That doesn't always work because there was like one example in BOM where one of the parameters to a function was not set within the function that called it, but it was set in the function that called that second one. And then it just left it in that same place. But yeah, that's in general a good idea. And you can also look in the function itself to see what registers are being read before they're written. So if you look in the function and you see it reading from RDX, for example, RDX you know is the third parameter, so probably that function takes at least 3 parameters. So you can look for clues like that. Good. And then parameters go in those 6, return values go in RAX. So how would we know if a function returns something? Kind of the same thing, right? We can look at the function itself to see if it puts anything in RAX. But it's also possible that it's just using RAX as a general purpose register. So you should also look at where the function is returning to see if RAX gets used right after. Yeah. Great. All right, let's finally talk about call E and call saved. So this is that this is that weird thing that confused everyone in lab. I think that's how most people remember it. So half of the registers are what we call call-er saved, and the other half are call-e saved. And the difference is who's responsible for preserving their value. So if we have, to make this more concrete, if we have a function f and a function g, if f calls g, then f is the call-er in blue and g is the call-e in yellow. So if it's a call-er saved register, that means it's the responsibility of the caller to save its value. So in particular, that means that the call-e, g, can use that register for whatever it wants. So if f cares about what's in that register, then f has to save it before it calls g. In contrast, a call-e saved register means it's g's responsibility to save its value. So if g wants to use that register, then g has to save it and then restore it before it returns. So here's an example. So on the left, R10 is a call-er saved register. So if f was using R10 for something, then it has to push R10 onto the stack to save it, and then it can call g, and g might overwrite R10. And then when g returns, f can pop R10 off of the stack to restore the saved value. Cool? And usually the stack is where these things would be saved. Call e saved, you'd see the same pattern, but it would be in g. It would be g pushing the register at the beginning of its function and then popping it right before it returns. Cool. So this is, again, you're not going to be writing assembly, so you don't have to, probably never in your life will you write assembly. Some people look relieved. So you don't have to know, like, in your head at all, like, which ones are call-er saved and which ones are call-e saved. But if you look at some assembly code and you see something like this on the right, like, g, why is it pushing this random register at the start of the function, then popping it again at the end? This is why that happens. So if you just trace the assembly, then you'll still follow what's going on. But this is why you get, like, extra things in the prologue and the epilogue to functions sometimes. Great. Okay. So now let's look at a whole function. You don't have to squint at this. I'm going to just broad strokes for now. So it's a function called sum. We have two of what we just talked about. We're pushing RBP and RBX. Those are both call-e saved registers. So that means this function, as it's the call-e because it was just called, it has to save them at the beginning. So this function must have decided that those two registers are necessary, so it's saving them to the stack at the beginning. Yeah. Exactly, yeah. It will only do this if it needs those registers. If it doesn't need to use them, there's no reason for it to save and restore the same value. And in particular, there are more than two call-e saved registers, so these must be the only two it needs. Okay. And then it looks like we're doing some math, and we're moving some things onto the stack. So it looks like that is initializing local variables. So these last two lines, we're moving 0 into those two registers that we just saved to the stack. So it looks like EBX and EBP are going to be two local variables stored in registers. And then the things above that, those other moves of 1, 2, 3, and 4, are moving things onto the stack. So that is probably a stack allocated array or something like that. So in general, local variables can be in registers or on the stack. And arrays don't fit in registers, so usually those would go on the stack. Yeah?
Does push automatically update the stack pointer?
Yes.
So why, you push twice and then you drop the stack pointer, but shouldn't the pushing already drop the stack pointer for 8 bytes?
Yeah, that's a good question. So pushing RBP will save to the stack and then move the stack pointer 8. Push RBX will move the stack pointer 8 again. And then that subtract 24 is for the rest of the stack for this function. So that 24 must be for local variables that this function is using besides the saved registers. And the reason it has to subtract explicitly there is because everything after that is a move. It's moving immediate values, so it's not pushing them. And it's more efficient in that case to do one subtraction than to do a bunch of pushes, is why I'm guessing it didn't explicitly use push. I don't know. A more optimized version of this function will probably look a bit different too. Okay. Then we have a jump and a jump down, a comparison, and a jump back. So that looks like a loop to me, right? Here we're jumping down to L2, and then we're comparing and jumping back to L3. So it looks like we're going in a circle. So that's probably a for loop or a while loop. Inside that loop, we see a call to printf. And before that call to printf, we're moving things into EDI and ESI and EBP. So we remember what EDI and ESI are for, right? Those are parameters. So it looks like we're going to call printf, and we're moving parameters into the registers that printf will read from. Yeah.
What is the $sign dot LCO? Is that a label?
That's a that's a reference to a relocatable immediate address. Don't worry about it. That's the short answer. You won't. I don't remember where I pulled this from. I don't think you'll see something like that on the final. But if you looked at the rest of the file, somewhere else in the file that this assembly function is included in would define what .lc0 was. And the compiler will sometimes leave things like that for the linker, and then the linker will fill in the actual addresses. Yeah?
You said that RBP and RBX in this case were local variables for the caller.
Yeah.
Not the caller.
Well, they're local variables for this sum function. And so when sum calls printf, sum becomes the caller. But before that, it was something else that called sum. So what thing is the caller and what thing is the callee is completely relative.
The caller of sum would own those local variables. Why?
No, sum would own them because sum is saving their values and then storing something new in them. So sum must be using them for something, whatever this function is doing with them. Cool. Okay, and then the loop itself has this comparison and this JLE. That's a conditional jump back. We'll talk more about loops. And then the epilogue is pretty much the opposite of the prologue. In the prologue, we had a push and a subtraction from RSP. And then we add to RSP, and then we pop and we pop. So it does the opposite. Cool.
Why doesn't a function just automatically try and use as many of the caller saved registers as possible instead of having to do extra operations if they want to use a calling saved register?
Normally it would, but if it only uses call E saved registers, then in particular, when we make this call to printf, printf could overwrite those registers as well. So it can't keep anything in a call E saved register like past the call to printf. So the reason it's using those two call saved registers as local variables is because then it can call printf and not worry about them getting overwritten. If you're not making any other function calls, then you're right, it would just use call eSaved registers. That would save a little bit of time. Oops. Wrong way. Okay. So some common patterns. If you have an if statement like the one on the left, it will compile to a comparison and a conditional jump, and then there will be so note here that it flipped the condition. So the original condition was A less than B. Here, this is A and B are not registers, so this is not exactly what the assembly would look like, but roughly. Instead of comparing A less than B, it's jumping if A is greater than or equal to B, so that's the opposite. So if that condition is false, then we jump to the else case. If that condition A less than B is true, then we just keep going and we do the if case. So the jump is a little bit backwards, but the thing and the other thing are in the same order. So just a subtlety to keep in mind. And then once we do the thing, we don't want to also do the other thing, so then we have an unconditional jump past the else case to whatever's after that. So we have two jumps, but both of the jumps go forward. This goes down here, this goes down here. So that's a good sign it's a conditional and not a loop, because loops look more like this. They also have two jumps, but this jump goes down and this jump goes back up. So it's more of a cycle. So while loops and for loops we can't really tell apart, because you could write a while loop and a for loop in C that do the exact same thing, and they would compile to pretty much the exact same code. Like that while loop on the left there, you could trivially rewrite that as a for loop, right? And the assembly would probably be exactly the same. So the one weird thing about loops is that GCC likes to put the condition at the end instead of at the beginning. So we jump down, and then we have this comparison down here, instead of the way it's written in C, where the comparison is at the top of the loop. So it jumps down, and then if the comparison is true, it jumps back to actually do the body of the loop. And then once the body of the loop executes, it runs directly into the comparison again. It jumps back. So it does that it flips the order because it's slightly more efficient. It means you only need one jump each time you iterate through the loop instead of two. You can think about that more on your own if you're curious. Okay, great. And we've seen some function calls. We have to, before we call a function, we have to set up parameters. We have to save any registers that we care about. Then we can call the function. Then when the function returns, we can restore the registers we care about if they're call or saved, and then we can reuse the return value, which we know will be in RAX. Yeah, that's it. All right, let's think about the stack a little more. How am I doing, guys? Am I going too quickly? I feel like I'm running through a lot of things. Good? Awesome. Okay. I didn't see any negative reactions, so I'll take that as a good sign. All right. So registers are great. We use registers whenever we can, but obviously we do sometimes need the stack, right? Because RAMs can hold a lot more stuff. So we keep things in registers when possible, but there are some cases where it has to go to the stack. So if we have, this is not a trick question, if we have a small number of local variables, what is it going to do? It's going to try to use registers, yeah. If there are only a few and they're not too big, then we'll just put them in registers because that's faster. but there are a couple special cases. If we have any local variables that we need to take the address of, registers don't have addresses, right? Only things in memory have addresses. So if we ever take the address of one of our variables, then that forces GCC to put that variable on the stack. So those variables will be on the stack. Just like in the function we saw before, some things were on the stack and some were in registers. And then if we have a lot of locals, or if we have large locals like arrays, that's what happened in the case that we just looked at. Then those also might have to go on the stack, because there are only so many registers, so eventually you're going to run out. And if it's a large variable like an array, it doesn't make sense to put that in a register either. Cool. Yeah. All right. More on the stack. We have these, I've been talking about these two special pointers, RSP and RBP. Normally, RSP as the stack pointer is used to keep track of the bottom of the stack or the end of the stack. And RBP is usually used to keep track of the beginning of the current stack frame, wherever that is. So if the stack is growing down, you can imagine ideally the base pointer would always point to the beginning of the current frame, the stack pointer would point to the end. So the stack pointer would grow down. And then we make a function call and the base pointer would go at the bottom of the stack and the stack pointer would grow down again for the new stack frame from there, and so on. That's the ideal, but GCC likes to cheat, again, as usual. So whenever it can get away with not changing these pointers, it will. So if you have a function that doesn't call any other function, it won't even change the stack pointer, because your function is growing down past the end of the stack, and then when it returns, your stack frame should be forgotten anyway. So there's no point in subtracting from the stack pointer and then adding right back to it again. If you do call other functions, though, then you have to make sure before you call them that the stack pointer is in the right place. So if you do call other functions, you do have to use RSP. And then RBP, similarly, most functions don't need to use that either. The one case where RBP matters is if the size of the stack frame isn't known in advance. So most functions will have a fixed size stack frame, like you'll know at compile time, this function needs 5 variables and they're going to take up 32 bytes, something like that. Then there's no reason to have RSP and RBP both updated, because if you need the beginning, you can always just use RSP plus 32, because you know exactly how big the frame is. But if you have a dynamically sized array, like an array whose size depends on something at runtime, then you don't know how big the stack frame is going to be. So then you have to keep track of the beginning and the end of the frame separately. So these days, that's the only time when GCC will use the base pointer. So again, you don't have to figure out yourself when and when not to use these variables, but if you see the stack pointer being used, that's usually what it's used for. If you see the base pointer being used, it's either as the base pointer or it's GCC is cheating again and it's a general purpose register. Yeah. Okay. So just for practice, let's think about writing some assembly just so that I can have fun. I don't care if you guys have fun. All right, so we want to take in one int, we want to add 5 to it and return the result. So what's the first thing that we should put in this function? Well, we have to add, right? Let's add. So remember, RDI is our first parameter register. So if at the beginning of foo, RDI will be our first parameter. We can just add 5 to it. Now RDI is 5 bigger. Now all that's left to do is return the result, right? What do we have to do to return that value? Exactly, yeah. RAX is the return register, so now we have to take that value and put it in RAX. So move, then return. That's it. Okay, good. This function isn't the most complex one you've seen. If you were really clever, you could actually use LEA to combine those two lines. Remember we talked about if you need to add and then store the results somewhere else, you can use LEA. GCC will do that here. We need to add 5 to EDI and then store it in EAX. And we can combine those two lines with one LEA, like so. So that's exactly what that does.
What is the L at the end of the LE?
That's a size suffix. I didn't talk about those in depth. There are, when it's not clear from context, there are sometimes suffixes to the instructions that determine how many bytes it's operating on. So L, the suffixes themselves are totally unintuitive. L is the 4-byte one. And that's also on the cheat sheet. So it basically means do a 4-byte addition and a 4-byte, and then store those 4 bytes in EAX, which makes sense. That's what you would want here because we're just working with 4-byte ints. And LEA is normally used for addresses, which would be 8 bytes, so it would make sense that we'd have to specify something else. Yeah.
What are suffixes on return mean? Because it's like it's actually, like you often see like what you do in ASF, does that mean it's like you move your block around?
Yeah, I don't really know why it has to do that. The question was, why do you sometimes see like retq suffixes on return? Something about the return address being not fitting in 4 bytes. I don't know. Don't worry about it. Okay, cool. A little bit harder. Oops. Suppose we want to write a function that returns the larger of its 2 arguments. So again, start off, 2 arguments will be an ESI and EDI, right? But now we need a conditional of some sort, like an if statement. So we can compare the 2 arguments first. And then we want to do one thing if one of them is larger and do something else if the other one is larger, right? So putting in a skeleton here, we'll compare the 2. We'll jump if EDI is greater down below. Otherwise, we'll run through. So we'll either do the first question mark or the second question mark. That's the goal. So now what do you want to put in that first question mark, say?
Move EDI to EAX?
Exactly, yeah. Then we did the comparison so we know which one is bigger. And so we just have to move it into EAX. But we have to be careful, right? That JG will jump if EDI is greater than ESI. So if EDI is the bigger one, then we'll jump down to the second question mark. If ESI is bigger, we'll be in the first question mark. So we actually want to move ESI into EAX, I think. And then in the other case, we want to move EDI into EAX. Does that make sense? Cool, okay. There's one more thing we're missing here. If we move ESI into EAX, if we don't do something, then we're just going to keep going to the next instruction. Then we're going to also move EDI, but we don't want that. So let's also add a jump past the else case. And then the last thing we need at the end is a return. Cool, and then we're done. So this is it's a very simple if statement that we constructed with an if case and an else case. Awesome. Now, of course, there's a pro version of this too because GCC is just super clever. Anyone have any guesses how it might do that? How it might do it better? I don't expect anyone to actually know. Okay. If you're GCC, you can also do this. which uses, it's cheating actually. It's using an instruction that you guys have not seen before. So this still does the comparison, and then it moves ESI into EAX. So this is assuming ESI is bigger, move ESI into EAX. And then C move GE is a conditional move, which is almost never useful except for right here where it's super useful. So C move GE is conditional move greater than or equal to. So if EDI is greater than or equal to ESI, then it will move ESI in and then it will overwrite it with EDI. But if EDI is not greater than or equal to, then it won't do this conditional move, and so ESI will be left there. So now we have the whole function without any jumps in just 4 lines. So you won't see that on the exam either, but I just thought it was neat. Cool. Okay. Any questions about how we came up with this sort of basic assembly? Okay, awesome. All right, so now here's the big example. This is going to be closest to what you might have to do on a final. And again, it'll be very similar to what you did on the second midterm, right? We might give you some assembly and expect you to answer questions about what the assembly does. So here's an assembly function on the left, and let's try to figure out what it does. So I like to do this in multiple stages because even I can't go directly, I can't read this directly and immediately figure out what the C code should be. So I have to think about it. Is there another class in here at 5? Yeah. Okay. That's awkward. Okay, I'm going to do this quickly. Is that okay? Okay, so we're going to skip down to the move. And so the first step I like to do is sort of write some assembly pseudocode to parse what each of the lines does separately. So I'm going through line by line, and I'm noting things as I see them. Cool. So now I haven't thought about variables at all yet, but I've made some observations. Sorry, I'm going quickly. So I notice RDI and RSI are both being used, so they must be the first 2 parameters. It looks like nothing else, so this function probably takes 2 parameters. Also note that in a lot of places RDI and RSI are dereferenced, like here and here. So they must be pointers. And all of those dereferences are with like that test B and compare B or single byte test and comparisons. So if we're always referring to single bytes, then they must be pointers to single byte data types, so probably char star. And then we have a loop, obviously. And it looks like up here, this loop is a slightly unusual structure, but it's still, because it has an extra label, but it's still looping back. And it looks like RDI and RSI, our 2 parameters, are both being incremented both times. And then we're comparing to see if the characters are equal. If they are, we keep going. If they aren't, then we skip to the end, right? So I just gave it away. Anybody have any guesses what this function is actually doing? Yeah, it's looping through 2 strings, character by character. It's comparing each character. And then it's returning an int at the end. So it must be strcomp. Good, yeah. And C code for that would look something like that. Okay, great. Any last questions? Awesome.
I've got one question.
Yeah.
Which is just the moves bizzle, which was on the other slide.
Oh, yeah.
And then we say like test of AL and AL. So that's just a test of something
The,
Or, I mean, yeah.
the move ZBL and move SBL are 0 extended and signed extended moves. So the move SBL is moving a 8-byte register into a 8-bit register into a 32-bit register, and the S means extend it with whatever the signed bit was. The move ZBL is moving. It's doing the same thing, but it's 0 extending instead of sign extending. Yeah, that's a good question, though.
Thank you.
So S for sign, B for byte, and L for 4-byte long. Okay, great. Yeah.